The seventh and final step, test and commission the motor, is usually the most complex. There are two ways to approach this step. You can select the Auto tab to choose to allow system setup to automatically perform the various components of testing and commissioning the motor, or you can select the Manual tab and specify parameters for and execute all of the tests yourself. The easiest way most likely will be to allow system setup to perform the tests automatically. You just click Auto and then Test Start to begin. If everything was completed successfully, you will receive a success message, and you can click Accept and move on. If not, you'll be forced to manually execute the tests. Sometimes you need to change various parameters of the tests in order to get them to finish properly. Let's look at all the parameters involved in performing the test manually. Click the Manual tab. See, the first test is called Open Loop Test. This test determines whether a positive voltage command to the motor produces a positive feedback response and a negative command produces a negative response. You can select the motor number here, the magnitude, which is a percentage of the permitted maximum output to the amplifier, the duration in milliseconds, which is how long to command voltage in the positive and then in the negative direction, respectively, and the number of iterations, where each iteration consists of both a positive and a negative voltage command. Next is the Measure DAC Bias Value Test. This commands an open loop zero output command, equivalent to Cout 0 or pound N out 0, where N is the motor number, and observes whether any motion occurs on the motor. If there is motion, it will adjust motorx.DAC bias in order to compensate until there is no motion when the open loop zero output command is issued. You only need to select the motor number and the number of iterations. Increasing the number of iterations may improve the accuracy of the DAC calibration, although the default of 2 is usually sufficient. I highly recommend performing this test before you perform the open loop test to prevent a runaway of the motor. Let's perform the Measure DAC Bias Value test now by clicking Test Start. It will measure the DAC bias and then write motor1.DAC bias, a value to eliminate the bias. Click Accept to take the change, and then we can try the open loop test. Let's try a conservative magnitude, about 5%, duration of 100 milliseconds, and 2 iterations. Then click Test Start. We see essentially exactly what we want to see. A positive open loop command indicated by the red line, and an increasing velocity indicated by the blue line, then a negative open loop command, and a decreasing velocity. And then on the second iteration, we see the same thing, meaning that our encoder direction is matching the output direction. If this is not what you're seeing, if perhaps you're seeing the opposite of this, where you observe a decreasing velocity with a positive open loop command, and vice versa, you probably need to go back to step 5, interactive feedback, and change your encoder-decode direction from clockwise to counterclockwise or vice versa. If you're seeing erratic movement, then possibly your wiring is incorrect, and you should check that as well. The last test is Tune Servo Loop. This test will move the motor and then estimate the gains required to control the motor based on the response. You should have the load connected to the motor before executing this test. Make sure that the load can move freely without physically damaging equipment or hurting anyone. For vertical axes, you should definitely configure the automatic brake enable features offered in PowerPMAX, motorx.pbrake, and associated structures. For this test, you can configure the magnitude of the output command to the motor as a percentage of the maximum permissible output, the duration to command the output in milliseconds, the minimum distance in counts the motor must move before attempting the estimation, and whether this motor is in velocity mode, in which case you should set velocity mode equals to 1, or torque mode, in which case you should set this equal to 0. For this test, let's assume a conservative magnitude of 5%, duration of 100 seconds, a minimum move size of 200 counts, and velocity mode is 0 because we are running this in torque mode. Then click Test Start. You should see the motor move a little bit. And then you will see a plot of the resulting step move. In this plot, you'll see the desired position command in the red line, the actual position response in the blue line, and the servo effort in the pink line. Below that, you will see the gains that PowerPMech has chosen for controlling the motor. If you are happy with this response, you can click Accept. If you are not, then you can actually go to the interactive tuning window and try to improve the tuning interactively or modify the auto-tuning parameters. For more details on improving the tuning, please see the tuning tutorial. But if you are happy with these gains, just click Accept, and you are done with commissioning your motor. Now, if you want to back up the motor parameters that were changed as a result of this setup process, go back to the main IDE program, and then in your Solution Explorer on the right side, under the Configuration folder, you can right-click that folder and then Generate Configuration File. Then you can name it something like Motor 1 Setup Complete. Then it will show only the motor parameters that have been changed from default. You can keep them in case you need to download them in the future. If you want to download this configuration file directly, right-click the file, click Check to Config Download, then right-click the configuration folder and click Download Config Files. Or you can just copy the parameters out of this file into another file, for example, in your Global Includes folder, for example, in globaldefinitions.pmh, and then when you build and download your project, these settings will be included in the download.